Hey guys, welcome to the supplemental lecture. Today we will cover general second order circuits and second order op amps. Give me just 1 second. Clearly not prepared here. Okay, so first of all, a very small amount of theory. So we have learned how to solve for the step response for series RLC circuits and parallel RLC circuits. But now what happens when you are faced with a circuit that doesn't fall into one of those neat categories? So the good news is that you can basically follow the prescription that we have been taking to date with step responses. And so assume that the circuit quantity that you're solving for is called X, obviously a function of time. That's usually going to be capacitor voltage or an inductor current. The first thing you do is you, as before, you will solve the circuit at 3 separate time points. At time 0 or time 0 minus, time 0 plus, and time equals to infinity. So the circuit at time equals 0 minus, because of continuity, will give you the initial condition X at time equals 0 plus. The circuit at time equals 0 plus should give you an initial condition for the derivative. So if it's a capacitor voltage that you're solving for, you will use the current through the capacitor to get the derivative of the voltage. If it's an inductor, you will get the voltage of the inductor to solve for the initial value of the derivative of the inductor current. And then time equals to infinity, that gets you the forced response. The second step is usually the one that requires the most work. So what you do here is you turn off your independent sources and solve for the ensuing natural response. What this usually means, and I'm going to do 2 examples for you guys here, is you have to write a KVL or KCL equation that will lead you to a second order differential equation. And when you get it to that second order differential equation, you solve for the roots. And you'll either have 2 real negative roots, 1 real root, or 2 complex roots. And based on that, you have your natural response, which you then combine with your forced response. So the forced response is just the value of X at time equals to infinity. So whatever the capacitor voltage ends up at the end of the universe, or whatever the inductor current ends up at the end of the universe. Okay, and then at the end, you combine your natural and forced response. That's your total response. And you use your initial conditions to solve for the constants that are going to be in the natural response term. If you don't understand what I just said, don't despair. I will let you read through the example that is done for you in the slide, and I will focus our attention on this example here. What I will do as before is minimize this. We'll blow up the screen as much as I can. And I will just move this. These tend to be very pretty involved. So I'm just going to make myself as much space as I can. Okay. So the first thing that we're going to do is to draw this circuit at time equals 0 minus. Okay, so time equals 0 minus. Remember, at time equals 0 minus, the circuit is in steady state. So what we have is our resistor. We have our open circuit capacitor. We have nothing in the middle because the switch is still open. We have our resistor. We have our short circuit inductor, right? So our inductor is here. And it's short-circuited because nothing at this time point, nothing in the circuit has changed for a very long time. And so now we need to come up with a value for the initial capacitor voltage, which is obviously going to be 0 volts because there's nothing energizing the circuit, as well as the initial inductor current, which is equal to 0 amps. There's no source, there was nothing stored, and so we have our initial conditions for the capacitor voltage and the inductor current. Next, we move on to just a smidgen of time later. Time equals 0 plus. So the difference here is that the capacitor is now not in steady state, and we have the current source is active because the switch below it is now closed. And similarly, the inductor is undergoing a transient. And so the key thing to note here is that these values, 0 volts and 0 amps, carry over to this time instant, meaning that there is 0 amps flowing through this inductor, and this capacitor is still at 0 volts. Why? Because of continuity. And so since there's no current flowing down the right branch, there has to be the full 2 amps is coming out of this current source, has to be flowing down the left branch, which is important because we can use that to get the initial condition for the capacitor voltage. Namely, we have that CV prime at time 0 is equal to 2. This is the expression for the capacitor voltage at all times, and at time 0, we know that it's equal to 2, because again, all of this current has to go left because none of it is going right, which means that I'm just going to maybe V prime 0 is equal to 2 over C. C is 1 over 20. So we have an initial capacitor voltage derivative of 40 volts per second. Similarly, we know that, this is probably the trickiest part, the voltage here is going to be whatever the drop is across this 10 ohm resistor, which is 20 volts. And this 20 volt voltage transfers all the way to the inductor. Why? Because there's no current through this resistor because there's 0 amps in this branch. And so the 20 volts here transfers to here, and finally all the way to here. Which means that we have an inductor voltage of 20 volts, which means that the initial inductor derivative is equal to 20 over L, which is equal to 10 amps per second. So these are the critical steps here to get the initial values for V and I. And then we also are going to solve this circuit at time equals to infinity. And so time equals to infinity, this is usually one of the easiest parts because the storage elements are in steady state again. Okay. And so this 2 amps obviously has to all flow over here. So it's gone all the way from the left to all the way to the right at time it goes to infinity. And so we easily see that the I of infinity is equal to 2 amps. Now, what about V of infinity? So what is the voltage between this point and this point? Well, notice that there's no voltage drop across this resistor, right? So basically, this capacitor ends up being parallel with this resistor, right? Because this resistor is dead because there's no current. So this terminal is effectively here, and this terminal is effectively here. And so the V infinity has to be equal to 2 times 4 is equal to 8 volts. All right. So now we have our initial condition, initial derivative, and our final condition. We are ready to go to solve for the natural response. So the natural response is made a lot easier by the fact that we disconnect the independent sources. And so our circuit will look like this. So this is 10, 4, this is our voltage B, this is our current I, okay? And so now is where you need to write a KVL equation. And to do that, I'm going to start out at this point here, and I'm gonna go clockwise. So let's write the KVL equation here. We have 4I, that's the voltage drop across the resistor, plus Li prime, that's the voltage drop across the inductor, minus V plus 10I is equal to 0. That's the KVL equation. So notice now we have one equation, two unknowns, obviously. And so now let's get our second equation, which we can get by looking at the capacitor. Namely, we know that the current through the capacitor, which is equal to I, because this is all a series circuit, has to be equal to negative CV prime. Why did I put it in negative? Because the capacitor, the positive end of the capacitor voltage is signified here. And so the current arrow hits the negative end. So now what I'm going to do is I'm going to substitute this equation into here. And what I end up with is minus 4 CV prime. I'm just going to leave the L's and the C's in there for now. I'll put them in just a minute. Minus LCV double prime minus V minus 10C V prime is equal to 0. I plugged in this directly into here. And now what I have is L times C is 2 times 1 over 20. So it's 1 over 10 V double prime. And then the V's have a 10C and so minus 10C and minus 4C. So that's minus 14C. So that's minus 14 over 20. And actually, let me just do something. I'm going to move everything over to the other side to make everything positive. So we have LCV double prime plus 14CV prime plus V is equal to 0. And now I put in my constants. L times C is 1 over 10 plus 14 over 20, which is, I'm just going to write a 7 over 10 plus V is equal to 0. And now multiply everything through by 10. Now my two roots are, so the roots of this polynomial, so this, if you write this as s squared plus 7s prime plus 10 is equal to 0. We have that s plus 2 times s plus 5 is equal to 0. And so our roots are s equals to -2 and s equals to -5. So that's huge because now we know that our natural response Vn of t is equal to a times exponential negative 2t plus b exponential negative 5t. And our total response is going to be Vn of t plus Vf of t, where f is forced, is equal to a exponential e negative 2t plus b exponential negative 5t plus 8 volts. So this is the final form. Oops. Okay. This is the final form of our total solution. We just need to get now the A's and the B's. So how do we get the A's and the B's? We do it as always. We plug in the initial conditions. So V0, which has to equal to A plus B plus 8, is equal to 0. And so we have that A plus B equals to -8. V prime of 0, which is equal to -2A minus 5B, has to equal to 40, I believe. Right. And so solving these two equations simultaneously, we get that A is equal to 0 and B is equal to -8. You can see that here. Just see. Right. So if you just try it, A plus 0 minus 8 is -8, and -5 times negative is 40. And so now we have basically everything we need to write the solution for V. It's going to be equal to, so A is 0, so this term comes out, and B is -8. So it's going to be -8 exponential negative 5t minus 8 sorry, plus 8, because the plus 8 comes here. And so we can factor this out. We can factor out the 8. We get 1 minus exponential negative 5t. So that's our solution for V. And so now the question is, we got our solution for V. How do we now get the solution for I? I don't want to have to do all that work again for I. Fortunately, you don't have to. And so what I'm going to do now is I'm going to selectively, let's see, what work, let me erase this part. So you want to look at the circuit at time equals to 0 plus. You want to look at the transient. Let's look at this time point. This is 2 amps here. This is I here. And this here is V. So we already have a solution for this, right? We have a full solution across all time for V of t. So now we can just write KCL at this point here, right? And the KCL is going to be I is equal to 2 minus CV prime. So let me just put it explicitly. Right, so why is it minus? Again, because the polarity here is flipped with respect to the current. So it's going to be equal to 2 minus 1 over 20, that's the C, times the derivative of this guy. And the derivative of this guy is equal to 40 exponential negative 5t, I believe. This is going to be equal to 2 minus 2 exponential negative 5t is equal to 2, 1 minus exponential negative 5t. Voila. Piece of work, right? Piece of cake, right? Piece of work was a Freudian slip there. All right. I'm going to leave this on for another second, and then we will move on to the second practice problem in this section. All right. So again, I'm going to let you enjoy the solved example here. And we will do this one. All right. This is one of the more challenging problems in the course. So it's also kind of a fun problem if you're a masochist. Let's just dive right into it. So first of all, what are we being asked to solve for? Here's the difference between this problem and the others is that here we're being asked to solve for a resistor voltage. So notice that resistors do not obey continuity, right? So we can't use all the steps that we have for the step response directly for V naught, right? The whole step response procedure where we get the initial condition, initial derivative, and the final condition, all of that applies to capacitor voltages and inductor currents because they obey continuity. Resistor voltages do not. However, this resistor happens to connect two capacitors. And so we know just from the get-go that V naught of t is going to be equal to V1 of t minus V2 of t. Right? And so let's carry the procedure forward for solving V1 and V of 2. And at the end, we're going to subtract them to solve for V naught. So same steps as before, starting with time equals 0 minus. Okay. And notice here, we don't have a source at 0 minus. We have a disconnected source. And our capacitors are open circuited. So I'm doing a messy job here drawing it. But the important thing is to note that this is ground. So this is 0 volts. And there's no current anywhere. There's not a complete path for the current to flow. And therefore, we know that V1 of 0 minus is equal to V1 of 0 plus is equal to 0 volts. And similarly, V2 of 0 minus is equal to V2 of 0 plus is equal to 0 volts. Because there's no current anywhere, so there's no voltage drops across these resistors, and so there's just a dead circuit. Now we flash forward to time equals 0 plus. And this is when the battery becomes active. So we're going to draw that. So this is the condition that you usually get to get your initial derivatives. And you will see that that is exactly what we're going to get. The resistors here are 1 ohm, which makes the math a lot simpler. This is V1. and this is V2. So notice here, this is 5 volts. And because of continuity, V1 is still sitting at 0 volts, and V2 is still sitting at 0 volts because of here. Right? These values carry forward because of continuity, which means that there's no current here. This is 0 amps. And there's a current of 5 amps flowing here. 5 minus 0, right? It's flowing that way. And this entire 5 amps has to flow through here. Has to go this way. So we have the C1. So I'm just gonna put it in. This is this capacitor. 1/2 times V1 prime 0 has to equal to 5, which means that V1 prime 0 is equal to 10 volts per second, right? Because the current, there's 5 amps flowing along this loop. And we know that CV prime has to equal to I, and that I is equal to 5, the C is equal to 1/2. So the initial derivative of the capacitor voltage is equal to 10 volts per second. And by a similar argument, right, there's no current flowing along the outside. And so we have that V2 prime 0 has to equal to 0 volts per second. So now we have our initial derivative. And then lastly, let's draw the circuit at time equals to infinity. So we have a circuit that still includes the battery, but now the capacitors are both open circuited. Oops. And so what you'll see in this case is that once again, there's not a complete path for the current to flow anywhere. But we do have a live voltage here. This is 5 volts, which means that this is 5 volts, and this is 5 volts. And so we know that V1 of infinity is equal to V2 of infinity is equal to 0 volts. Sorry, 5 volts. Okay, so now we have our initial condition for the both capacitor voltage, the initial derivative of both capacitor voltage and their final voltages. So now we are ready to proceed to the natural response. So what I'm going to do, I'm going to just erase this. Ooh, I didn't mean to do that. Okay, so I'm just going to write that underneath to make myself some room. And I'm going to take care of the natural response up here. So the natural response circuit will look like this. Where this is V1 and this is V2. And this is ground. This is 1 ohm. This is 1 ohm. So and this is 1/2. This is 1/3. Okay. Let us try to come up with 2 equations. And I'm going to tell you that the way to come up with the 2 equations here is to apply KCL at node 1 and node 2. So let's write KCL at node 1. We're going to have, let me see if I can draw the current arrows for you guys. So we're gonna have current flowing this way. Oh, I wanted to do flowing this way, flowing down, flowing right, and flowing down. Okay, and let's KCL at node 1 is minus V1 over 1 is equal to 1/2 V1 prime plus V1 minus V2, right? This is the current flowing down the first capacitor, and this is the current flowing between here and here. So when you rearrange that, you get that V1 prime plus 4V1. Let me just do all the steps. It's going to be equal to 1/2 V1 prime plus 2V1 minus V2 is equal to 0. And so we get V1 prime plus 2V1 1 minus 2V2 is equal to 0. And now let's apply KCL at node 2, which is even more straightforward. Just V1 minus V2 over 1 is equal to 1/3 V2 prime. So we have V1 minus V2 is equal to 1/3 V2 prime. And this is where we can isolate for V1. V1 becomes V2 plus 1/3 V2 prime. And the key step is here that we can substitute this in, we can substitute this into here. And then what we're going to be left with is an equation that only has V2 terms. And so if you substitute, you get the following. You get V2 prime plus 1/3 V2 double prime plus 4V2 plus 4 over V2 plus 4 over third V2 prime minus 2V2 is equal to 0. And again, collecting like terms, we get 1 over third V2 double prime and 7 over plus 7 over 3 V2 prime and we have plus, and I'm going to write 2 as 6 over 3. And that way we have V2 double prime plus 7 V2 prime plus 6 V2 is equal to 0. And so this, your characteristic polynomial is s squared plus 7s2 plus 6 is equal to 0, which means that s plus 6 times s plus 1 is equal to 0. And so your roots here are s equals to minus 6 and s equal to minus 1. And so the natural response is Vn, this is for V2. So it's going to be A times exponential negative 6t plus B times exponential negative t. Okay, so that's the natural response. Because I need space, I'm going to need to erase, let's see, erase up here. Keep this. Okay. So now I am going to write the full response for V2T. So this is the natural response. And my steady state response for V2 is here, 5 volts. So I have, right, V2T is going to be equal to A exponential negative 6t plus B exponential negative t plus 5. And so now we need to get my A and B coefficients. And so I get my A's by plugging in t is equal to 0. So V2 of 0 is A plus B plus 5, which means that A plus B is equal to minus 5. And V2 prime at 0, which is equal to negative 6A minus B, has to equal to 0. And so when I solve these two equations simultaneously, I get that A is equal to 1 and B is equal to negative 6. You should verify that for yourself, which means that my expression for V2T is equal to exponential negative 6t minus 6 exponential negative t plus 5. That is my solution for V of 2. But what I need, unfortunately, is V naught. And to get V naught, I also need to get the solution for V1. Fortunately, there is a very straightforward relationship between V1 and V2. Namely, we have that V, so if you just apply KCL at this node here, you get that V1t minus V2t is equal to 1/3 V2t. And so we have an expression for V2. So it means V1 of t is equal to V2 of t plus 1/3 V2 prime t. But we have an expression for V2t up here. And so now I'm going to actually try to do the math here for you just to convince you, right? So let's write this out. Let's take V2 of t, V1 of t is equal to V2 of t, which is exponential minus 6t minus 6 exponential minus t plus 5 plus, I'm going to do this over here, I'm sorry. 1/3 the derivative of V2t, which is minus 6 exponential negative 6t plus 6 exponential negative t. And let me just, so I have that V1 of t is equal to, let's exponential negative 6t minus 6 exponential minus t plus 5 plus, sorry, minus 2 exponential negative 6t plus 2 exponential negative t, which equals to, stick the 5 out front. And how many, so we have minus exponential negative 6t minus 4 exponential negative t. And finally, we know going all the way back to here, v1 of t minus v2 of t, right? It becomes minus big bracket. Now I'm going to write the expression for v2 of t, which is exponential negative 6t minus 6 exponential negative t plus 5, close big bracket. That becomes, the 5 comes out. And what you're left with here is minus 2 exponential negative 6t plus 2 exponential negative t. And that is your final answer, which matches up here. So this was a lot of work. And you do have a posted solution. Hopefully this helped. Again, this is one of the more challenging problems in the course because you have to basically solve 2-step responses and then combine them to get V naught, which is their resistor voltage. All right. So we are not going to cover the second order op amps circuit section in this course. So I'm going to stop the video here. And once again, I hope that this helped. And I look forward to seeing you guys all back here on Monday for the last lecture of the semester.